Hey everyone, welcome to Quantlock. Today we're diving into literally one of the most fascinating engineering hurdles in modern physics, quantum error correction. Because building a quantum computer isn't just about controlling atoms inside of fridges that are colder than deep space. It's actually a high-stakes detective game. We're going to explore this brilliantly clever system known as the surface code. How do you fix a computer that literally breaks the moment you look at it? To understand why this is such a crazy detective game, we have to kind of understand the core paradox of quantum computing. Think about your everyday laptop. If a bit accidentally flips from 1 to 0, your computer kind of just looks at the memory, spots the error, and boom, it fixes. But a quantum bit, a qubit, it's different. It exists in this incredibly fragile state of superposition. It's a 0 and 1 at the exact same time. And the fundamental law of quantum mechanics is that the second you directly observe or measure that state, the superposition collapses. It's completely destroyed. And to make matters worse, qubits don't just suffer from normal bit flips. They also get hit with phase flips, which is this totally new and unique quantum error. So how on earth do we fix an error that we aren't even allowed to look at? To shield these incredibly delicate quantum states, scientists came up with literally brilliant topological solutions. Instead of relying on just one physical qubit to hold one piece of information, the surface code takes a single logical qubit and spreads it across a massive two-dimensional grid. Now what's really interesting about this slide is that the checkerboard layout you're seeing, the dark gray dots sitting on the edges, those are the data qubits. They hold the actual quantum info, but check out the blue and orange dots in the center of those squares. Those are our parity qubits. What essentially acts is this intricate interlocking web of alarms. Their whole job is just to constantly interact with the data qubits around them, sensing if anything has gone wrong and acting as a real-time protective shield. So the way these alarms actually work is through something called syndrome extraction. Think of a syndrome like a set of clues left behind by a crime scene. By performing these super carefully choreographed quantum gate operations, the parity qubits act like little detectives. They investigate the neighborhood around the data qubits. They're extracting info about the parity, basically just checking if the number of ones in that little local area is even or odd. But here's the kicker. They do this without even measuring the actual 1 or 0 value of the data qubits themselves. We get all the clues we need to fix the errors, but that super fragile quantum state, it stays completely undisturbed. And what makes this whole checkerboard setup so incredibly robust is how it handles those two totally different types of quantum errors we mentioned earlier. The bit flips, which we call X-type errors, and the phase flips, or Z-type errors. The code actually gives different jobs to different squares on the board. The light squares, the X stabilizers, are uniquely designed to spot those Z-type phase flips. And then flip it around, the dark squares with the Z stabilizers are built to catch the X-type bit flips. By alternating these across the entire grid, the surface code creates this perfect interlocking web of detection. Honestly, no matter what kind of error hits the board, an alarm is absolutely going to trip. Let's walk through the real-time life cycle of one of these quantum errors. Step 1. A rogue burst of energy or maybe just a tiny calibration flaw causes an error on a single data qubit. Step 2. The very next time the system runs a check, the neighboring parity qubits sense a change and boom, the parity check fails. Step 3. This failure generates our syndrome, a literal bit string of zeros and ones that represent our clues that get instantly zapped out of the super chilled quantum fridge to a regular classical computer. And finally, step 4. A classical algorithm that figures out what just happened and mathematically reverses the error. You guys, this entire 4-step cycle has to happen ridiculously fast. We're talking millions of times a second, over and over again, just to keep the computer running. So we've got all these alarms tripping all over the place, spitting out this massive stream of binary clues, but how do we actually make sense of them? Well, the go-to tool for the job is a minimum weight perfect matching algorithm, or MWPM for short. See, every time an error happens on a data qubit, it trips the alarms on two neighboring parity qubits, so errors pretty much always show up as a pairs of defects. And if a bunch of errors happens right next to each other to form a chain, well, only the alarms at the ends of that chain will actually trigger. The MWPM algorithms are detective. It takes this crazy chaotic map of flashing endpoint alarms and starts connecting the dots. It basically assumes that nature is lazy, meaning the most likely cause of those alarms is just the shortest possible path of errors between them. It literally draws the shortest line between the clues and tells the system, hey, here's your error chain. But you know, the reality of the detective work is actually way more complicated because errors don't just happen in a physical space on a checkerboard, they happen in time. The physical gates and the measurements we use to check the alarms, they're not faulty themselves. So if an alarm triggers, is it because the data qubit actually had an error, or did the alarm itself just glitch out? To figure that out, the decoder has to track the surface code across a three-dimensional lattice, mapping the grid across multiple cycles of time. An error might show up on an alarm, going off in one physical spot, but blinking on and off across 3 consecutive time cycles. So our decoder has to thread the shortest path through this incredibly complex 3D space-time maze just to uncover the invisible error chain. It's a massive puzzle. As brilliant as the system is, the checkerboard shield definitely has its absolute limits, and this brilliantly illustrates what we call a spanning path, crossing from one side of the lattice to the other. Remember how we said the decoder always guesses the shortest path between 2 alarms? Well, what happens if a really long chain of physical errors happens, one that spans more than half of the board? The alarms at the end of that long chain are going to trigger. The decoder sends those alarms, assuming the shortest path between them, and tries to apply a correction, but because the actual error was that longer path, the decoder's correction ends up connecting the ends of the error chain, completely linking one side of the surface code boundary to the exact opposite side. When that spanning path happens, the system doesn't just fail to fix the error, it accidentally flips the entire overarching logical qubit. The detective got totally fooled, and the data is eventually and ultimately lost. So to quickly summarize how the whole code can just break down. Just like we saw, if an error chain is longer than half the distance of the code lattice, the decoder is mathematically guaranteed to guess wrong and cause a logical failure. The classical decoders themselves can just fail to keep up, or they might misinterpret those crazy 3D space-time clues. But the third point is probably the most critical for the hardware we have today. A lot of our mathematical proofs showing that surface codes work are based on probabilistic noise, like neat random errors. But in the real world, hardware suffers from general unstructured noise like correlated errors or calibration drift, and research actually indicates that for truly general noise, we don't even have a guaranteed fault tolerance threshold yet. The noise might just overwhelm the entire system. But despite all those vulnerabilities, the field is definitely still not standing still. We're actually modifying the classic surface code to survive the harsh reality of real-world quantum noise. One of the absolute biggest breakthroughs have come from just observing how real qubits actually misbehave. In a lot of these top quantum architectures like superconducting qubits or trapped ions, errors aren't just perfectly random, they suffer from what's called biased noise. Basically, Z errors or defacing happen way more frequently than X or Y errors. So instead of using standard decoder that treats every error exactly the same, researchers are turning into advanced maximum likelihood or ML decoders. They're even slightly modifying the checkerboard itself, measuring products of Y instead of Z just to specifically target this biased noise. It's like they're tailoring the shield to defend against the exact weapon the environment is using. For standard surface code dealing with completely random noise, the theoretical threshold where error correction even becomes possible is around 10.9%, but by adapting the code to purely biased noise and using this advanced ML decoders, researchers have demonstrated a leap all the way up to a massive 43.7%. That means the code can tolerate nearly 4 times as much noise and still protect the information. It just completely proves that by customizing our error correcting codes to the actual physics of our hardware, we can unlock massive efficiency gains. It's a real game changer. So this is exactly why, despite the massive computational headache of decoding all those clues and a clear vulnerability with those spanning paths, the surface code is still widely regarded as the undisputed champion of quantum error correction. A big part of that is a simple grid structure and geometric locality. That just means qubits only ever need to talk to their immediate nearest neighbors on a 2D grid. That makes something we can actually physically build in a lab today. You don't need impossibly long tangled wires crossing all over the place. You just need a nice flat checkerboard. We've seen the sheer brilliance of the topological checkerboard. We've talked about the massive challenge of threading the needle through the 3D space-time clues, and we've looked at the incredible innovations that tailor the code to real-world physics. The surface code really is the bridge between fragile quantum theory and robust quantum reality, but it all leaves us with one ultimate question. As our classical algorithms get faster and our physical qubits get slightly cleaner, will the surface code be the key that finally unlocks the era of scalable, world-changing quantum hardware? Thank you so much for joining me on this video. Keep questioning the quantum world, and I'll catch you next time.